Hi kids, time for another video. So, we're gonna start our last topic of the whole freaking semester, and it is going to involve triple integrals. So I do want to review a little bit about triple integrals. So that's why I don't want you to do anything with this. Just want you to transform it into cylindrical coordinates. Remember, cylindrical coordinates is when you have symmetry around the z-axis and you can basically do polars with z height. So hopefully you recognize that you can change the bounds here. The first bound, the z bounds, square root of x squared plus y squared is square root of r squared, or just r. And then for the y's, you've got a whole circle with a radius of 2. And then to go all the way around, you're going to go from 0 to 2 pi. So you're going to get this integral, but I have to then change the inside, right? So the inside is going to be, instead of x squared plus y squared, what's it going to be? Right? This is just going to be r squared. Sorry about the pen there. And this is going to turn into r dr d theta. Right? So there, just some review of cylindrical. So yes, with triple integrals, you might have to do dy dx dz, or some variation of, combination of those, or spherical or cylindrical. So recall that Stokes' theorem allowed us to evaluate a surface circulation integral, right? See if I can get rid of this thing. Instead of a line integral. So we would have our right? As long as we had a closed, that's what that circle around there, as long as we had a closed, simple closed curve, calculating the work done to go around it was equal to summing up all the curl on the surface dotted with the normal, right? The dot product on the surface. So circulation line integral, circulation surface integral. Total circulation around, little bits of curl circulation on the surface with a boundary that is still that curve C. And remember, Stokes told us the surface doesn't matter. Think about, I read a nice little analogy where, like those big soap bubbles, right? If you dip one of those big circular wands down into soap and pick it up, right, that surface film is flat, but if you blow into it, you can make the bubble. But the boundary stays the wand. So that's what Stokes allows you to do, is to just calculate this curl on the surface dotted with the normals and add them all up. And that's going to be the same as the work done to go around the line. So there's a picture of a circle in a curve in a vector field, and dotting, right, assuming you're parametrized, your surface or your curve there, dotting the tangent dr with the force field. How well are the tangents aligned with the force field? And then for the circulation, it's all those curls all along the surface, whether that surface is flat or not. I took that curve, that red curve that is in 3D space, and we're calculating the curl on it. Again, this comes from George Stokes, who actually, I didn't know, is a first baronet or baronet, Sir George Gabriel Stokes. And he was Irish. How about that? Right? Pretty cool. So today we're going to talk about the Gauss divergence theorem, which is relating flux, not curl, not the surface integral that is just flux, with divergence. So remember, the flux is the tendency of the vector field to flow outward from a curve, or a region contained by that curve, right? Along the curve, Again, the tendency of the vector to align with the normals, that's what the flux is. But divergence measures the outward flow at each individual point within that region. So adding up all those teeny tiny bits of divergence gives us the same value as flux. That's what Gauss proved. The divergence theorem relates the outward flow of the force field through the surface to the sum of the divergence of the force field within. So, in other words, right, again, see if I can make this pen work. Where is it? There it is. If I'm on this surface, right, how the force field coming through here, how well does it align with the normal coming out there? But notice this is surface 1 of this shape. Here's surface 2. Here's the back of it is surface 3. The front of it is surface 4. Here's surface 5. I mean, right? There's so many surfaces that you'd have to calculate the flux integral over to add it up over the whole thing. Or what Gauss said is that you can just instead go to the inside, and measure at every single point here, at every point inside this solid, what is the sink or source, right? The divergence going in or out, sum up all those divergence values inside, and you will equal the flux of the vector field going through, flowing through each of those 6 surfaces. That's pretty powerful because who wants to do 6 surface integrals, right? So this is what Gauss's divergence theorem says, that a surface integral, flux integral, the force dotted with the normals, that's our flux surface integral, which measures the total outward flow through the surface, is the same thing as the flux volume integral, which totals the sum of little bits of outward flow in V inside the volume, which is divergence. So if you're doing a triple integral, though, remember the price to pay. It is nice, instead of doing 6 double integrals, you can only do 1 triple, but remember to do a triple integral, you might be in, it might be a spherical cylindrical shape, cylindrical conical shape, or a bunch of planes, right? And so you might have to integrate with spherical and your spherical price, your cylindrical and your cylindrical polar price, or your rectangular. So again, to find the total flux and flow of a force field through a closed surface, it does have to be closed, and I'll show you some pictures of that in a minute. Use the divergence theorem to evaluate a volume integral instead of computing possibly multiple surface flux integrals, right? Look at these shapes from geometry. Sphere is pretty nice. There's just one surface, right? One surface, but a cube has a whole bunch of cuboid, the pyramid, the cone even. The cone has the top, but it also has that bottom plane, right? The cylinder has 3 surfaces, the top, the bottom, and then the side, right? So a lot of surface integrals, and instead you can do 1 volume. So look, notice that circle around the double integrals. It says the same thing that we did with green, right? And we don't always put that, because the assumption, if you're going to use the Gauss divergence theorem, or the GDT, as cool people say, it has to be closed. So the flux coming out of a surface is equal to the sum of all the sources and sinks at each point within a surface. But the divergence theorem does require that you're smooth and closed, and piecewise smooth. So I think of this as water, right? Like, would water be contained on any surface here, right? No, right? The water would just fall off of here, right? It would just spill off. It would fill up here, the water would be contained until it got too full, and then it would spill out. But in each one of these surfaces, the water would stay in, right? So not closed, closed. So I do have a handout that I've attached to the to the email with these problems typed up. Excuse me. So use the Gauss divergence theorem to evaluate a flux integral, just like we did with Stokes' theorem. What that says is don't evaluate the double integral. Use Gauss to turn the double integral, the double right flux or surface integral, into a triple volume. So the first thing I need to know is this surface closed? And it is, right? It's a paraboloid capped by the xy plane, right? So it's got a solid bottom. It's not going on infinitely. So instead of doing the surface integral, I'm going to do the triple integral of divergence. And remember, divergence is just a sum. It's not, it's just a dot product, right, of the partials. So the divergence of my force field F is the partial of x cubed with respect to x, the partial of 2xz squared with respect to y, and the partial of 3y squared z with respect to z. Oh, those animations were supposed to come in differently. So, right, I have 3 times x squared y squared, which is why I osmosis this 3 out here. Right, this 3 here is with the x squared y squared. And since I thought about this as cylindrical, right, being it's symmetric across the z-axis, I'm going to integrate with respect to z, going from the xy plane 0 all the way up to the cone. Right, the top of the cone, 4 minus x squared minus y squared. And I'm going to integrate x squared plus y squared with respect to z. And so hopefully you can see what I did. Right, it was just x squared plus y squared z, where I plugged in 0, and 4 minus x squared. Well, I plugged in 4 minus x squared minus y squared and then 0, which made it go away. Then I went into, now I'm down to a double integral, and I went into polars. And that's, you can see what I have there. Right, I did go to polars because I felt pretty cold. And I got negative 32 pi. And I was done. All right, example 2. Again, this says use the divergence theorem. It could also say use the Gauss divergence theorem. It could say use the GDT. Any way that they are telling you to use to calculate a surface integral to get the flux, right? But look at my shape. My shape is closed, but look how many surfaces I have. That's so many surfaces. I do not want to do a surface integral for each of the different surfaces, right? I've got, right, this surface here. I've got this surface here, and then I have the floor. I mean, oh my gosh, right? I just don't want to deal with all of that. So instead, I'm going to turn this into a triple integral. The divergence of the force field, partial of xy with respect to x, is just y, partial of y squared plus e to the xz squared with respect to, oops, I dropped a parentheses there, didn't I? Is just 2y, and then the partial of sine xy with respect to z is 0, right? So I just got y plus 2y, aka 3y. So there again is my surface. Let's see if you can figure out what I did there. Right, I osmosis the 3 out, so I didn't have to mess with that. And then I did stay rectangular, right? Because of that, this slicing down through, I didn't have symmetry around the z-axis. I wasn't going to do conical, or I'm certainly not in a sphere. So if you can tell how I got these values, right? I chose to do y first, saying y goes from 0 out to this plane, right, which is 2 minus x. And then z is equal to 0. I started here at 0 and went up to that paraboloid thingy. And then the x's, of course, went from 1 to -1. So that's how I figured out all of my bounds. And now I'm just going to go, right? I'm just going to go ahead with my integration. So as you can see, I already have the first line up where I integrated. I got y squared over 2. And then I was plugging in y equals 0, plus first y equals 2 minus z, and then y equals 0. And that's what I got. Now I'm going to integrate that with respect to z. Right, so I have 2 minus z is my u, right? I was doing u substitution up here. U equals 2 minus z, so du was equal to negative dz, and that's why this negative is right here. Right, so I osmosis this 2 out, and that's where this 2 happened. And then I was integrating again with respect to z, so I did my z cubed, really my u cubed, over 3. So I have 2 minus 1 minus x squared. And then I plugged in 1 minus x squared and 0. And of course, plugging in 0 didn't wipe it out because I had that, right, 1 minus 0 squared right over 3. And that's where the 8/3 came from. Then I integrated with respect to x, right? I kind of just multiplied all that out. I didn't show that work, right? Actually, I didn't integrate yet. I multiplied all that out and got this nice thing. I will not make you multiply out something cubed on the test, but just to show you where this came from, I integrated. That was just power up, x to the 7th over 7, 3x to the 5th over 5, 3x cubed over 3 minus 7x. And that's what I got when I was done. So here, notice that it asks you to do the GDT to evaluate the flux integral. And I have 3 surfaces. Z equals a cone, but that cone looking thing, or that paraboloid looking thing, goes from only 1 to 4. Then I have a cylinder, x squared plus y squared is equal to 1, but it is then capped underneath with z equals 0. So I don't want to do 3 surface integrals. I'm just going to do 1 volume integral. I'm going to find the divergence of my force field, which is nice because I just ended up with 1. Now I have 2 different volumes, really, right? So the triple integral of 1 dv, I'm going to break up into z going from 0 to 1, and then z going from 1 to the top of that paraboloid. But I can use property of integrals since the 1 matches, and just do that, right? But my integrand is just a 1. So this just becomes z, plugging in 4 minus 3x squared minus 3y squared, and 0. Being a little chilly. So I did 4 minus 3r squared, r d theta. Of course, my radius is 0 to 1 and going all the way around, 0 to 2 pi, right? Because I felt chilly. And I got 5/2 pi out of it. All right, here we go. Last one. Find the flux through the vector field, yada, 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 which looks terrible, right? Doesn't that vector field look awful? Over the sphere with a radius of 2. So I'm not going to do a surface integral because I'd have to parametrize, find the normals, all that kind of stuff. I'm just going to do the divergence of my vector field, right? And the first term is x plus sine z, but the partial with respect to x is just 1. Partial of 2y plus cosine x with respect to y is just 2, and the partial of 3z plus tan y with respect to z is just 3. So I got 6. So there's my sphere. Now I'm going to hopefully realize, since it is a sphere, I'm going to go to spherical coordinates, right? 6 is my integrand, which of course I can osmosis out, and then I have to pay the spherical price, right? To transform into spherical space, I have rho squared sine phi, and then d rho d phi d theta. And since everybody is constants, right? My radius is 2, so rho goes from 0 to 2. Phi, remember, is measured from the positive z-axis and has to be between 0 and pi, and it's the entire sphere. So I'm going from 0 to pi, and then theta goes all the way around, 0 to 2 pi, and then ends up to be, right, certainly you know the first one, 0 to 2 pi is 2 pi, and then integrating sine gives you negative cosine, so you have plugging in pi and 0, you get a 2, and then integrating rho squared is rho cubed over 3. Plugging in the 2 gets me 8/3. And that's 64 pi. However, my friends, since I can osmosis this 6 to the outside, right? Take that 6, pull it out here. Then since my integrand is just a 1, it is just the volume of this sphere. And I took middle school and I paid attention. And the volume of a sphere is 4/3 pi r cubed, with of course the 6 out front. And shocker, I also get 64 pi. Cool. All right. So enjoy. Hopefully you watch this or when we come back, assuming that we're going to be back on Thursday, we will have our staying with 16.9, do another day of Gauss divergence theorem. Friday, we will then review the unit. All right.